downtown Chicago, 2025. Water flows through cast iron pipes installed in 1908, 117 years old and still running strong. Meanwhile, across American suburbs, PVC pipes installed just 30 years ago are already cracking, leaking, and heading for costly replacement. The numbers make no sense. How did pipes built by our great-grandfathers with molten iron outlast everything we've engineered since? 1905, Birmingham, Alabama. Steam hisses from Red Mountain foundries as European pipe-making experts arrive to inspect American operations. For 500 years, European foundries had perfected iron pipe casting, the proven methods that built water systems from London to Paris. These Birmingham upstarts, led by a 35-year-old Christian industrialist named John Joseph Egan, claimed they could revolutionize pipe making with zero experience in metallurgy. European wisdom said it was impossible. American ambition said otherwise. In the coal-dusted workshops of Alabama, something was about to challenge centuries of tradition and create infrastructure that would outlast every modern innovation that followed. The European method had ruled pipe making for 5 centuries, and in 1905 nobody questioned its dominance. From London to Paris, from Berlin to Birmingham, every major water system flowed through iron pipes cast in deep sand pits, using techniques perfected by medieval guild masters. The process seemed as unchangeable as the tides. Molten iron poured vertically into sand molds, cooled for 18 hours, then extracted with massive overhead cranes. Production rates never exceeded 12 pipes per day, and every foundry accepted this limitation as the price of proven quality. James McWane understood this reality better than most. As president of Pittsburgh's largest pipe consortium, he commanded respect across American foundries through 3 decades of methodical expansion. McWane's operation imported not just European techniques, but European expertise, hiring German foundrymen and British metallurgists to ensure American pipes met old-world standards. His factories produced steady profits using methods that had built empires, and he viewed innovation with the skepticism of a man who had seen countless improvements fail spectacularly. When news reached Pittsburgh that Southern investors were financing a new pipe plant in Birmingham, McWane's response carried the weight of established wisdom. "These Birmingham upstarts think they can reinvent metallurgy itself," he declared to his board of directors. "It's proven technology that built every major city in Europe." But in Birmingham, Alabama, Charlotte Blair saw opportunity where others saw impossibility. As the only woman on Alabama's corporate boards, she had spent months analyzing railroad shipping reports and foundry production data that revealed a startling truth. Southern iron ore from Red Mountain tested higher in purity than Pennsylvania deposits, while Birmingham's coal seams provided fuel costs 30% below northern competitors. Blair possessed an almost supernatural ability to recognize market trends, and she understood that geographic advantages meant nothing without visionary leadership to exploit them. Her choice for company president defied every convention of industrial experience. John Joseph Egan arrived in Birmingham with zero pipe-making knowledge but unshakable faith in American innovation. At 35, this Christian industrialist read his Bible every morning and treated business decisions as moral choices, believing the Golden Rule applied as much to foundry floors as church pews. Egan's background in agricultural equipment had taught him that mechanical systems could be improved through systematic observation, and he possessed an intuitive understanding of how American workers responded to shared ownership and democratic decision-making. His vision for the American Cast Iron Pipe Company challenged not just European methods but European philosophy: build pipes stronger, faster, and cheaper, while creating America's first truly worker-owned industrial democracy. Birmingham offered perfect conditions for this experiment. Red Mountain iron ore could be mined, processed, and transported to foundries within 5 miles. Coal seams ran everywhere, providing fuel at costs that made northern competitors envious. Limestone quarries supplied flux materials, while rail lines connected Birmingham to every major American city. When ASIPCO's first pipes rolled out in May 1906 using traditional pit casting methods, success seemed inevitable. The initial numbers supported this optimism. By November 1906, ASIPCO employed 209 workers and shipped 6,380 tons of pipe to customers across the South. Cities from Atlanta to New Orleans placed orders for Birmingham iron, impressed by competitive pricing and delivery times that beat northern foundries by weeks. Egan implemented profit-sharing policies revolutionary for American industry, creating genuine partnership between management and workers that produced extraordinary dedication on foundry floors. But the fundamental limitations of pit casting soon revealed themselves through brutal mathematics. Each pipe required 18 hours to cool in sand molds, creating production bottlenecks that prevented rapid order fulfillment. Wall thickness varied wildly around pipe circumferences, from half an inch to 1.2 inches on identical pipes, because off-center cores shifted during vertical pours. Most critically, slag and impurities collected at the top of each casting, requiring removal and disposal that wasted 15% of expensive molten iron. European buyers rejected ASIPCO samples for inferior American finish, claiming Birmingham pipes lacked the precision of German or British alternatives. When the recession of 1907 struck American industry, these technical limitations became financial catastrophe. Orders plummeted 60% as cities delayed infrastructure projects, while established pipe companies launched aggressive price wars designed to eliminate upstart competitors. McWane's Pittsburgh consortium spread rumors that Southern iron was second-rate metal produced by amateur foundrymen with more ambition than expertise. They could afford to slash prices temporarily, knowing their established customer relationships and proven European methods would outlast any Southern challenge. By winter 1907, even Egan's original investors questioned his leadership. Board member William Blair, Charlotte's own brother, privately wondered whether some innovations were better left to those who had perfected them over centuries. The pit method built the Roman aqueducts, he reminded skeptical investors. It built London's water system and Paris's distribution network. Maybe some things are simply perfected already. Egan faced the crushing reality that good intentions could not overcome fundamental engineering limitations. European foundries had optimized pit casting through 500 years of gradual refinement, achieving production rates and quality standards that represented the absolute ceiling of the technology. No amount of American determination could eliminate the physics of vertical casting, the cooling time, the wall thickness variations, the slag waste, the production bottlenecks that made European methods simultaneously proven and limited. Standing on ASIPCO's foundry floor as winter winds swept across Red Mountain, Egan understood that matching European performance would never be sufficient. American industry needed breakthrough innovation, not incremental improvement. Somewhere beyond the proven wisdom of centuries lay engineering solutions that could revolutionize pipe making entirely. The question that would define his company's survival was whether American ingenuity could discover them before Birmingham's experiment collapsed under the weight of old-world expertise. For 11 years, ASIPCO struggled against the fundamental limitations of pit casting, while European competitors dominated American markets with techniques perfected over centuries. Egan's worker-owned company survived through sheer determination and profit-sharing policies that created extraordinary loyalty, but survival was not victory. Production remained bottlenecked at 18 hours per pipe, wall thickness variations plagued quality control, and slag waste consumed 15% of every molten iron pour. The mathematics of vertical casting seemed as immutable as gravity itself. Then in 1918, news arrived from an unexpected source that would shatter every assumption about pipe manufacturing. A French-Brazilian inventor named Dimitri Senso de Lavaux had filed patents for something revolutionary: centrifugal casting. Instead of pouring molten iron into stationary vertical molds, de Lavaux proposed spinning horizontal molds at tremendous speed, using centrifugal force to distribute metal evenly against mold walls. European foundries dismissed the concept as experimental fantasy from a colonial outsider, but Egan recognized opportunity where others saw impossibility. De Lavaux's insights emerged from observing everyday physics that foundrymen had ignored for centuries. Watching laundry spinning in washing machines, he understood that centrifugal force could overcome the gravitational limitations that plagued vertical casting. His Brazilian laboratory experiments proved that spinning molds at precise speeds eliminated the slag accumulation, wall thickness variations, and cooling delays that made pit casting inefficient. While European guild traditions rejected innovation from outside their established circles, American industrial culture embraced breakthrough thinking regardless of its source. W. D. Moore, ASIPCO's methodical plant supervisor, approached Delavod's principles with the systematic analysis of a chess master studying new opening strategies. Moore had spent decades mastering traditional casting techniques, but his engineering instincts recognized that centrifugal force could solve problems that 5 centuries of incremental improvement had failed to address. Working 18-hour shifts in Birmingham's foundry, Moore translated abstract physics into specific shop floor procedures that ordinary workers could master. The American adaptation began with careful study of Delavod's patent specifications, then evolved through systematic experimentation that combined Brazilian innovation with Alabama engineering pragmatism. ASIPCO engineers developed their own monocast method that improved upon the original concept, pouring molten iron at 2,800 degrees Fahrenheit into sand-lined mold spinning at 850 revolutions per minute. The physics were elegant in their simplicity. Centrifugal force drove liquid metal outward against mold walls with 60 times the force of gravity, creating uniform distribution impossible with vertical pours. The first test pipe revealed results that defied decades of foundry experience. Wall thickness remained uniform within 1/16 inch around the entire circumference, precision that pit casting could never achieve. No slag waste accumulated because spinning action forced all impurities to the inner surface, where they could be machined away cleanly. Most remarkably, production time dropped from 18 hours to 3 hours per pipe, eliminating the cooling delays that had bottlenecked traditional methods for centuries. Moore's engineering team documented every aspect of the breakthrough process with methodical precision. Mold preparation required new techniques for applying sand linings that could withstand centrifugal forces without breaking apart. Poor timing became critical. Molten iron had to enter spinning molds at exactly the right temperature and speed to achieve optimal distribution. Temperature control systems needed complete redesign to maintain consistent heat throughout the accelerated casting cycle. Each innovation built upon centrifugal foundation principles while solving practical challenges that emerged during real-world production. By 1920, ASIPCO's transformation was measurable in hard numbers that impressed even skeptical competitors. Daily production reached 50 pipes compared to the previous maximum of 12. Wall thickness consistency improved by 400% across all pipe diameters. Quality control tests showed centrifugal pipes were 40% stronger than pit-cast alternatives, with dense metal structure that resisted corrosion and pressure stress far better than traditional methods produced. The breakthrough enabled manufacturing capabilities that had seemed impossible under European methods. ASIPCO began producing 24-inch diameter pipes, larger than any European foundry could manufacture using pit casting techniques. The centrifugal process scaled efficiently from 6-inch residential pipes to massive 24-inch municipal mains, maintaining consistent wall thickness and strength characteristics across the entire range. Workers developed specialized skills for managing high-speed molds, precise temperature control, and timing sequences that required split-second coordination. Building momentum accelerated as American cities recognized the superior performance of centrifugal cast pipes. Detroit placed orders for 50,000 feet to support urban expansion that traditional foundries could not fulfill within required time frames. Los Angeles requested ASIPCO's largest pipes, 24-inch diameter giants, to carry water across the San Fernando Valley, trusting Birmingham engineering for infrastructure projects that would serve millions of residents. Even European cities began requesting American pipes, acknowledging that centrifugal casting had surpassed traditional methods in both quality and production capacity. Innovation multiplied as ASIPCO engineers explored additional applications for centrifugal principles. They introduced cement lining applied during the spinning process. Why? Creating perfectly smooth interior surfaces with corrosion resistance that extended pipe lifespan by decades. Mechanical joint development eliminated the need for lead caulking, using rubber sealing systems that provided superior flexibility and leak resistance. Each advancement built upon the centrifugal foundation, proving that breakthrough innovation created opportunities for continuous improvement. The economic transformation was equally dramatic. Production costs dropped 30% compared to pit casting, while quality improvements commanded premium pricing from customers who understood superior value. Birmingham's plant operated 24 hours with 3 shifts, employing 800 workers who shared in company profits through Egan's revolutionary ownership structure. By 1922, Oxipco produced 200,000 tons annually, while distributing $2.3 million in profit-sharing payments that created genuine prosperity for foundry families. The centrifugal advantage seemed unstoppable, vindicating Egan's faith that American innovation could surpass European tradition through systematic application of scientific principles. But industrial revolutions create vulnerabilities alongside opportunities, and Oxipco's dependence on visionary leadership was about to face its ultimate test. Success bred confidence, and by 1921, Oxipco's centrifugal revolution had transformed American pipe manufacturing from European imitation into global leadership. Orders flooded Birmingham from cities that had once trusted only German or British foundries, creating production schedules that pushed the Alabama plant to maximum capacity. The worker-owned company's profit-sharing payments reached unprecedented levels, distributing genuine prosperity among foundry families while proving that industrial democracy could compete with traditional corporate hierarchies. Detroit's massive infrastructure expansion required 50,000 feet of Oxipco pipe to support population growth that strained existing water systems. City engineers, initially skeptical of Southern manufacturing claims, became converts after testing samples that exceeded European quality standards by measurable margins. The centrifugal process produced pipes with consistent wall thickness, superior strength characteristics, and corrosion resistance that promised decades of reliable service. Detroit's order alone employed Birmingham workers for 6 months, while generating profits that exceeded Oxipco's entire first-year revenues. Los Angeles presented an even more ambitious challenge: 24-inch diameter pipes to carry water across the San Fernando Valley, supporting the city's explosive growth during the 1920s real estate boom. No European foundry could manufacture pipes of this diameter using traditional pit casting methods, which created market opportunities that only centrifugal technology could fulfill. Oxipco's engineers designed specialized handling equipment for these massive pipes, each weighing over 2 tons and requiring precise manufacturing tolerances to ensure proper joint alignment across miles of pipeline. The technical achievements multiplied as Birmingham's foundry pushed centrifugal casting beyond its original limitations. Cement lining application during the spinning process created interior surfaces smoother than hand-polished European alternatives, with corrosion resistance that extended operational lifespans by decades. The centrifugal force distributed cement uniformly across pipe interiors, eliminating the thickness variations and weak spots that plagued manually applied linings. Flow characteristics improved dramatically. Water moved through cement-lined centrifugal pipes with friction coefficients 30% lower than traditional cast iron surfaces. Mechanical joint development represented another breakthrough that built upon centrifugal foundations. Oxipco engineers eliminated lead caulking requirements by designing rubber sealing systems that provided superior flexibility and leak resistance. The precise wall thickness control achieved through spinning enabled standardized joint dimensions that simplified field installation while improving long-term reliability. Municipal engineers reported installation times reduced by 40% compared to traditional lead-caulked joints, with leak rates approaching 0 even decades after installation. European recognition arrived grudgingly, but definitively as Old World cities began requesting American pipes for critical infrastructure projects. London's Water Authority placed orders for Oxipco's 24-inch mains, acknowledging that centrifugal casting had surpassed traditional methods in both manufacturing precision and production capacity. Paris followed with specifications for pipes that European foundries could not manufacture within required timeframes, trusting Birmingham engineering for infrastructure serving millions of residents. The economic transformation created industrial prosperity that validated Egan's vision of worker ownership as competitive advantage. Production costs had dropped 30% below traditional methods, while quality improvements commanded premium pricing from customers who understood superior value. Birmingham's plant operated continuously with 3 shifts, employing 800 skilled workers whose profit-sharing payments created genuine middle-class prosperity in the heart of Alabama's industrial district. Annual production reached 200,000 tons by 1922, with distribution networks spanning from coast to coast. But industrial leadership created dependencies that seemed invisible during periods of growth and success. John Joseph Egan's visionary guidance had transformed every aspect of ASIPCO's operations, from technical innovation to worker relations, creating a company culture that reflected his personal philosophy of Christian industrial democracy. His daily presence on foundry floors, his systematic approach to engineering challenges, and his unwavering commitment to employee ownership had become integral to the company's identity and competitive advantage. The first signs of Egan's declining health appeared during the intensive production schedules of 1922, when 18-hour days took their toll on a constitution already weakened by hereditary tuberculosis. His father's early death from the same disease had haunted Egan throughout his career, creating urgency about proving that worker-owned companies could build lasting industrial empires. The irony was brutal. Success itself was accelerating the physical decline that threatened everything he had built. March 1924 brought the catastrophe that competitors had predicted and workers had dreaded. John Joseph Egan collapsed from tuberculosis complications and died at age 54, leaving behind a revolutionary company but no clear succession plan for maintaining its innovative culture. The man who had challenged European foundry traditions, created America's first worker-owned industrial democracy, and revolutionized pipe manufacturing through centrifugal casting was gone at the peak of his achievements. Wall Street's response was immediate and merciless. Stock prices of competing foundries surged as investors bet against the Birmingham experiment, assuming that visionary leadership could not be replaced by institutional systems. James McWane's Pittsburgh Consortium, which had spent nearly 2 decades watching Southern upstarts capture market share through superior technology, launched aggressive price wars designed to exploit ASIPCO's leadership vacuum. McWane publicly claimed that centrifugal methods had died with their founder, spreading rumors that spinning techniques created metal fatigue and structural weaknesses. Customer confidence wavered as established foundries offered dramatic price reductions to cities considering ASIPCO contracts. Orders began canceling as municipal engineers questioned whether worker-owned companies could maintain quality standards without charismatic leadership. The pipe failure in Cincinnati, actually caused by improper installation procedures, was blamed on Birmingham's spinning methods by competitors eager to discredit centrifugal technology entirely. ASIPCO's stock price fell 40% within 6 months of Egan's death, creating financial pressure that threatened the profit-sharing programs and worker ownership structure that had made the company unique. Industry observers predicted inevitable acquisition by traditional foundries, assuming that innovative manufacturing techniques could not survive without the visionary leadership that had created them. The test of American industrial democracy was beginning, and the outcome would determine whether breakthrough innovation could institutionalize beyond individual genius. The crisis deepened through the summer of 1924 as competitors exploited every vulnerability created by Egan's death. McWane's Pittsburgh Consortium coordinated a systematic campaign to undermine confidence in centrifugal casting, spreading technical rumors designed to create doubt among municipal engineers who had embraced Birmingham's innovations. They claimed that spinning created microscopic stress fractures, that high-speed rotation caused molecular instability, and that metal fatigue would manifest after just a few years of service, accusations impossible to disprove without decades of operational data. The Cincinnati pipe failure became a weapon in this propaganda war, despite clear evidence that installation errors had caused the break. A contractor had failed to properly bed the pipe, creating stress concentrations that would have destroyed any casting method. But McWane's engineers presented the failure as proof of centrifugal casting's inherent weaknesses. Technical reports circulated among city engineers claiming that Birmingham spinning methods produced pipes with internal defects, invisible to standard testing procedures, but guaranteed to cause catastrophic failures. Orders canceled with devastating speed as municipal authorities chose proven European methods over innovative American techniques that suddenly seemed risky without visionary leadership to guarantee their reliability. Detroit delayed its expansion project, citing engineering concerns about new manufacturing processes. Los Angeles suspended its pipeline contract pending additional technical review of centrifugal casting methods. Even smaller cities that had praised ASIPCO's superior performance now questioned whether worker-owned companies could maintain quality standards without charismatic founders to ensure excellence. The financial pressure threatened everything Egan had built to protect his workers and their families. ASIPCO's stock price continued falling as Wall Street analysts predicted inevitable acquisition by traditional foundries with established customer relationships and proven European methods. Profit-sharing payments that had created genuine middle-class prosperity for 800 foundry families faced suspension as revenues plummeted 40% below production costs. The worker ownership structure that had made the company unique seemed like a luxury that survival could not afford. But Egan had anticipated this exact crisis and prepared for it through legal structures that protected his vision beyond his own mortality. His 1923 will placed all company stock in a permanent employee trust, eliminating outside shareholders who might demand short-term profits over long-term innovation. No quarterly earnings reports to nervous investors. No board members representing financial interests that conflicted with worker welfare. No pressure to abandon centrifugal technology for quick returns to traditional methods. The worker owners controlled their own destiny completely. W.D. Moore emerged as the natural leader during this crucial transition, combining technical expertise with deep understanding of Egan's industrial philosophy. As plant supervisor, Moore had translated centrifugal principles into practical shop floor procedures, earning respect from workers who trusted his engineering judgment and commitment to their welfare. His methodical approach to problem-solving provided stability during the chaos of leadership transition, while his intimate knowledge of centrifugal casting enabled authoritative responses to competitor attacks. Moore's first decision demonstrated the intellectual courage that would define ASIPCO's survival strategy. Instead of retreating from innovation, the company would double down on engineering excellence. While competitors spread rumors about centrifugal casting defects, ASIPCO would institute the most rigorous testing program in the industry to prove superior quality through measurable data rather than marketing claims. Every pipe would undergo pressure testing at 500 pounds per square inch, double the normal requirement and beyond any municipal specification in America. The testing regime revealed what Moore's engineering instincts had suspected. Centrifugal casting actually eliminated the defects that plagued traditional pit cast iron. High-speed rotation forced impurities to pipe interiors where they could be machined away, while centrifugal pressure created dense metal structures with fewer air pockets and inclusions than vertical casting could achieve. Wall thickness uniformity meant consistent strength characteristics around entire circumferences, eliminating the weak spots where pit cast pipes typically failed under pressure stress. Metallurgical analysis conducted by independent laboratories at Cornell University provided scientific validation for what ASIPCO's practical experience had demonstrated. Centrifugal pipes showed grain structures with superior density and fewer internal defects than European alternatives. Tensile strength exceeded traditional cast iron by measurable margins, while corrosion resistance improved due to the uniform metal distribution that spinning achieved. The accusations of metal fatigue proved groundless. Centrifugal casting actually created stronger, more durable pipes than any alternative method, but technical superiority meant nothing without customer confidence, and rebuilding trust required patience that worker-owned companies could afford while profit-driven competitors could not. ASIPCO's employee trust structure provided crucial advantages during this period of market skepticism. Without external shareholders demanding immediate returns, the company could invest in long-term quality demonstration rather than short-term cost-cutting measures that would compromise centrifugal advantages. The vindication began slowly, but gathered momentum as operational data accumulated from pipes installed during ASIPCO's peak years. Cities that had received Birmingham pipes in 1920 and 1921 began reporting back with performance comparisons that demolished competitor propaganda. ASIPCO pipes showed less corrosion, maintained better pressure characteristics, and required fewer repairs than European pipes installed during the same period using traditional methods. Detroit's Water Authority issued a technical report comparing centrifugal pipes installed in 1921 with German pipes from 1919. After 3 years of service, the ASIPCO pipes showed virtually no corrosion, while the German alternatives displayed typical oxidation patterns that would require replacement within decades. Flow rates through centrifugal pipes remained consistent due to smooth cement linings, while traditional pipes showed decreased capacity due to internal corrosion and scale buildup. Municipal engineers who had initially embraced centrifugal technology began defending their decisions publicly, providing authoritative testimony that countered competitor rumors with operational evidence. The American Society of Civil Engineers invited Moore to present technical papers documenting centrifugal advantages, lending professional credibility to manufacturing methods that competitors had attempted to discredit through fear rather than facts. By late 1925, the tide had turned decisively in favor of engineering truth over marketing manipulation. Cities that had canceled orders during the crisis began returning with new contracts, acknowledging that centrifugal casting had proven itself through performance rather than promises. The worker-owned company had survived its ultimate test, demonstrating that American industrial democracy could preserve innovation beyond individual leadership through institutional commitment to excellence. By 1925, orders returned with unprecedented strength, as municipal engineers recognized that operational data had vindicated every claim about centrifugal casting superiority. Cities that had experimented with competing products during ASIPCO's crisis period switched back to Birmingham pipes after discovering that traditional methods could not match the performance standards that spinning technology delivered consistently. The worker-owned company became profitable again while proving definitively that American industrial democracy could compete with any corporate structure when built on engineering excellence rather than financial manipulation. The turnaround accelerated as infrastructure projects delayed during the leadership transition resumed with expanded specifications that only centrifugal casting could fulfill. Detroit's Water Authority not only reinstated its original 50,000-foot order, but doubled the contract size to support suburban expansion that required larger diameter pipes than European foundries could manufacture. Los Angeles completed its San Fernando Valley pipeline using exclusively ASIPCO 24-inch mains, creating a distribution network that would serve millions of residents for generations, while demonstrating American engineering capabilities on a scale that impressed international observers. Technical innovations continued evolving as Moore's engineering team explored applications that built upon centrifugal foundations. They developed specialized techniques for casting pipes up to 36 inches in diameter, giants that required custom handling equipment and mold modifications that pushed spinning technology beyond its original limitations. The physics remained elegant. Centrifugal force at 850 revolutions per minute created wall densities of 7.2 grams per cubic centimeter compared to traditional pit casting's 6.8, while maintaining uniform thickness within 1/16 inch tolerances across circumferences that measured over 9 feet. The cement lining process achieved perfection through systematic refinement that eliminated every variable that could compromise interior surface quality. Spinning molds received precise applications of Portland cement mixed to exact consistency specifications, then rotated at controlled speeds that distributed material uniformly while centrifugal force pressed cement against pipe walls with pressures impossible to achieve manually. The result was interior surfaces smoother than polished steel, with corrosion resistance that would extend operational lifespans by decades compared to unlined alternatives. International recognition arrived as European cities acknowledged American leadership in pipe manufacturing technology. London's Metropolitan Water Board placed orders for ASIPCO's largest diameter mains, specifying centrifugal casting requirements that no British foundry could meet using traditional methods. Paris followed with contracts that trusted Birmingham engineering for infrastructure serving the French capital's growing population. Even German cities, despite nationalist preferences for domestic manufacturing, requested American pipes for projects where centrifugal quality advantages justified premium pricing. The real test of durability began revealing itself through systematic monitoring of pipes installed during ASIPCO's earliest years. Birmingham's original 1906 installation, cast using traditional pit methods before centrifugal innovation, showed typical corrosion patterns that would require replacement within 50 to 60 years. But pipes installed after 1920 using spinning technology displayed remarkable preservation with minimal oxidation and structural integrity that promised century-long service life under normal operating conditions. Chicago's infrastructure provided the most compelling evidence for centrifugal superiority. ASIPCO pipes installed in 1908 using early spinning techniques continued carrying water with pressure characteristics unchanged after 17 years of service. City engineers conducted detailed inspections that revealed interior surfaces virtually identical to installation conditions, with cement linings intact and metal walls showing negligible corrosion despite Chicago's harsh climate and aggressive water chemistry. The engineering reality became undeniable through comparative analysis that demolished every argument against centrifugal casting. Traditional pit cast pipes required wall thicknesses of 1 full inch to achieve adequate strength, while centrifugal techniques produced superior performance with 3/4 inch walls due to uniform density distribution. The material savings alone reduced costs per foot while improving handling characteristics that simplified installation procedures and reduced labor requirements for municipal projects. Production efficiency reached levels that vindicated every prediction about American manufacturing superiority over European methods. ASIPCO's Birmingham plant produced 200 pipes per day using centrifugal techniques, compared to the maximum 12 pipes that traditional foundries could achieve with pit casting. The speed advantage compounded through reduced cooling time, 3 hours versus 18, that enabled rapid order fulfillment impossible with vertical casting methods that had dominated the industry for centuries. Quality control systems developed by Moore's team established standards that exceeded anything attempted in traditional foundries. Every pipe underwent pressure testing at 500 pounds per square inch, metallurgical analysis for grain structure consistency, and dimensional verification that confirmed wall thickness uniformity within tolerances impossible to achieve through pit casting. The systematic approach to excellence created customer confidence that no marketing campaign could duplicate. As the 1920s progressed, ASIPCO's success validated Egan's fundamental insight about worker ownership as competitive advantage. Employee profit sharing reached unprecedented levels as the company's market dominance generated revenues that traditional corporate structures would have directed toward shareholder dividends. Instead, foundry workers earned middle-class wages supplemented by annual profit distributions that created genuine prosperity throughout Birmingham's industrial district. The technological legacy extended far beyond pipe manufacturing as other industries recognized centrifugal principles could revolutionize casting applications across metallurgical spectrum. Steel companies adopted spinning techniques for producing seamless tubing, while automotive manufacturers used centrifugal methods for engine components that required precise wall thickness control. The innovation that had transformed water infrastructure became foundation technology for American industrial leadership in multiple sectors, but the ultimate validation would require decades of service life to demonstrate fully. ASIPCO pipes installed throughout the 1920s carried water through American cities while their creators aged and retired, confident that centrifugal casting had solved fundamental engineering problems that had limited infrastructure durability for centuries. The spinning technique that had emerged from Brazilian innovation and American adaptation created pipe networks designed to serve communities for generations, proving that breakthrough technology could deliver on its most ambitious promises when developed through systematic engineering excellence rather than marketing hyperbole. The foundation was laid for infrastructure that would outlast every alternative that followed, creating urban water systems built to serve the 20th century and beyond.